Welcome to the Deep Dive, where we unpack complex topics and really get to those crucial nuggets of knowledge you need.
Glad to be here.
Today, we're plunging into the intricate world of large language models, LLMs, and a really significant challenge they face as they get, well, bigger and more useful.
That's right. As LLMs become more powerful, they're being used for increasingly complex things. Think deep document analysis, very specific in-context learning, or even advanced code generation using huge amounts of documentation.
Right.
And these applications, they demand that the models process incredibly long inputs, what we call long context lengths.
You're basically asking an LLM to digest, I don't know, a whole encyclopedia set or write code based on hundreds, maybe thousands of pages of API docs all at once?
Exactly. The amount of information the model needs to sort of hold in its head is just immense.
But here's the catch, the bottleneck, right? The longer that input context, the more expensive and slower the LLM inference gets.
Right. It's like trying to remember every single word of some enormous book while also trying to answer a very specific question about it accurately and fast. That's the core problem this research tackles.
And that's why we're doing this deep dive today. Our mission is to rigorously explore this academic paper, Squeezed Attention, Accelerating Long Context Length LLM Inference.
Yeah, we're going to follow the paper's structure pretty closely, break down the abstract ideas, the innovative approach, how they actually built it, and the results they found, just like you'd analyze a groundbreaking scientific paper.
Okay, so let's start at the beginning. Why do these modern LLM applications even need to handle such huge amounts of information? Why the long context?
Well, the need is pretty fundamental for these advanced tasks. Take in-context learning. You give the model examples right in the prompt to show it how to behave for a new task. More context means better, more relevant examples.
Okay.
Or think about complex question answering on documents. The LLM needs to pull details from potentially anywhere in a very long text.
Right, the answer might not be conveniently located at the start.
Exactly. Same for code generation. Providing lots of API docs or existing code as context, it can dramatically improve the code it writes. So basically, more context helps tailor the model, condition it for specific, precise outputs. It gives the model the richest environment to work in.
So without long context, these powerful applications just wouldn't be nearly as good.
Yeah.
You mentioned that bottleneck. What exactly makes processing these long contexts so inefficient and expensive? What's the real pain point?
The core issue is the, explosion of computational resources needed. Memory capacity, and especially memory bandwidth, required for LLM inference just skyrockets as context lengths go up.
And the paper points to something specific.
Yes, the main culprit is what's called the KV cache. During attention, the model stores key value pairs for every token in the input sequence.
Okay.
And as the sequence length grows, this KV cache grows linearly. So you double the context length, you roughly double the KV cache size. This leads to huge inefficiencies, massive memory usage, and sky-high operational costs. You can almost picture the engineers pulling their hair out over the server bills.
That paints a picture. So it's not just the calculations themselves, but storing and fetching those intermediate values that becomes the choke point.
Precisely. Memory bandwidth often becomes the limiting factor.
And the paper makes this really important distinction about the type of context, which seems critical to their solution. Can you break that down?
They do, and it's absolutely key. They differentiate between two main types. First, there's fixed context.
Fixed context.
Right. This is a large chunk of the input that usually stays the same across different user requests. Think system instructions, big chunks of documentation, maybe those few showed examples you feed in once at the start of a session. This part can be really, really long.
So it's the foundational stuff, the boilerplate, that doesn't change every time I ask a new question.
Exactly. And then you have the user input. That's the dynamic part, the actual questions or prompts the user provides, which get tacked on to the end of the fixed context. Okay.
The problem, as the paper points out, is that the attention computation for this massive fixed context usually dominates the whole inference time. It's the biggest piece, and it's processed again and again.
Which brings us neatly to their core idea, squeezed attention. So what's the big idea here? How do they tackle this fixed context issue?
The core idea is, well, pretty clever. Squeezed attention is designed specifically to speed up that attention computation for the fixed context part.
Okay.
The basic premise is that for many applications, a lot of that fixed context is actually, redundant for any specific query. You don't need all of it all the time.
Makes sense.
So instead of making the LLM churn through every single key value pair in that huge fixed context every single time, why not figure out and use only the most relevant bits?
That feels intuitive. Like searching an index instead of reading the whole book. But how is this different? Other methods have tried to, drop less important tokens or something, haven't they? That's a great point, and it highlights what's novel here. Some older methods might look at physical proximity tokens close together, or just make a one-time decision to discard tokens deemed less important. Squeezed attention uses semantic similarity.
Semantic similarity, meaning?
Meaning it groups tokens based on what they mean, their conceptual relationship, even if they're physically far apart in the text. This is powerful because related ideas aren't always neighbors in a long document, right?
Absolutely. Apple on page 10 and fruit nutrition on page 500 could be linked. So how does this work at a high level? The paper is abstract and figures must give a clue.
Yeah, high level, it's sort of a three-step dance. First, there's an offline clustering step. This happens before any real-time inference.
Okay, offline. So it doesn't slow down the user's experience.
Exactly. In this phase, they take the keys from the fixed context and group them using k-means clustering based on that semantic similarity we just talked about. Each group then gets represented by a single key centroid. Think of it as a summary vector for that cluster's meaning.
A representative for each group of ideas. Got it. What's step 2?
Step 2 is online retrieval. This happens during inference when a user query actually comes in. Instead of comparing the query tokens to potentially millions of individual keys in the fixed context,
Which would be slow.
very slow, it compares the query tokens to that much, much smaller set of key centroids. This lets it quickly predict which groups of keys, which centroids, are semantically relevant to the current query.
Faster lookup. And the final step.
The third step is exact attention. Once it identifies the important keys via those relevant centroids, the actual attention calculation is performed only with those keys. This drastically cuts down on memory bandwidth and computation.
Fewer keys to deal with.
Precisely. And they also propose a hierarchical version, which we can get into, that makes it even more efficient, potentially reducing complexity from linear to logarithmic.
Logarithmic, wow. Okay, let's unpack the algorithm more. Phase 1, that offline clustering. How does that work in practice? They use k-means.
Yep, phase 1, the offline part. It's a one-time setup cost. They use k-means clustering, specifically on normalized key vectors. Normalizing helps ensure the clustering focuses purely on the semantic direction, not just magnitude.
Okay.
And the crucial output is that each cluster gets its representative centroid, which is just the average of all the key vectors in that cluster. This centroid then acts as a proxy, a stand-in for all the keys it represents.
And you mentioned it can group keys that aren't next to each other.
Yes, that's a key advantage over methods that just look at local windows. Semantic similarity can span the entire document.
Okay, phase 2.
Yeah.
Online. Query-aware key retrieval. The user asks something. How does it use those centroids to quickly find what's relevant now?
Right, this is inference time. So instead of query versus all keys, it's query versus centroids. Much faster. They introduce something called a softmax estimate. They denote it psi, which basically gauges the average attention score a query would likely give to all the keys within a specific cluster.
Sort of like, how important is this whole group of keys likely to be for my current question?
Exactly. It's an estimate of the cluster's relevance. Then they use a threshold.
A threshold.
Yeah, they apply a global threshold to these estimated softmax values. Psi. If a cluster's estimated importance is above the threshold, the system decides, okay, this cluster seems relevant, and it retrieves the actual keys belonging to that cluster.
And if it's below?
If it's below the threshold, it just skips retrieving those keys entirely, saving bandwidth and computation.
Clever. And they mentioned this threshold adapts.
Yes, that's another smart part. The global threshold adapts implicitly to different attention heads. Some heads might have attention spread out quite evenly, while others might focus heavily on just a few keys.
Ah, so it doesn't need separate tuning for every single head.
Right. By using this global threshold on the softmax estimate, it naturally retrieves more keys from the more balanced heads and fewer from the very peaky, skewed heads. It's efficient resource allocation without lots of manual tweaking.
Okay, and you mentioned hierarchical lookup earlier. How does that push the efficiency even further, especially for really, really long contexts?
Yeah, the hierarchical part is where it gets really interesting for massive scale. It's about getting the best of both worlds. the accuracy you get from fine-grained clusters, but the lookup speed you get from coarser ones.
How do they structure that?
Offline, they do multi-level clustering. First, they cluster the keys into, say, level 2 centroids. These are pretty fine-grained. Then they take those level 2 centroids and cluster them into level 1 centroids, which are much coarser.
Okay, so it's like chapters and then paragraphs within chapters, a nested structure.
That's a great analogy. Then, during the online retrieval phase, the query first compares itself against the very small set of level 1 centroids. This lets it instantly rule out huge chunks of the context that are clearly irrelevant.
Pruning the search space quickly.
Exactly. Then it only drills down further, comparing against the level 2 centroids within those level 1 regions that looked promising. Finally, it identifies the specific important keys to retrieve. It's a much faster way to zero in on what matters.
And this has a big impact on the complexity, you said.
A huge impact. Let's look at the theoretical complexity. Baseline LLM inference, as we said, is OL, linear, with context length, L. Memory compute, it all scales linearly. Bad news for long contexts.
Right.
With the one-level squeezed attention retrieval, the complexity becomes OC plus K. C is the number of centroids, K is the number of keys you actually retrieve. Since K is designed to be much, much smaller than L, and C is also much smaller than L, that's already a big win. OC plus K is way better than OL.
Significant improvement.
And the hierarchical one.
That's the logarithmic magic. Hierarchical retrieval complexity becomes OC log L plus K. Here, C is the number of coarse level 1 centroids, which is even smaller than C, and crucially, the dependency on the original context length L is now logarithmic, thanks to that hierarchical search.
Log L instead of L.
Yes. For extremely long contexts, millions of tokens going from linear to logarithmic scaling is the difference between something being computationally feasible and, well, basically impossible or incredibly expensive. It's a massive leap in scalability. That's a huge theoretical win. But theory is one thing. Did they actually build this? You mentioned optimized kernels. That sounds like serious engineering work.
They absolutely did. This isn't just an algorithm on paper. They implemented efficient custom compute kernels using Triton, which is a language for writing GPU code. They built kernels for the two main stages.
Okay, what were they?
First, a kernel for the centroid lookup, that fast comparison between query tokens and the centroids. They optimize this heavily, parallelizing across attention heads and query tokens, even making it work well for the tricky case of generating just one token at a time, which can be hard to parallelize efficiently.
And the second kernel?
The second is for sparse attention. Once they've identified the important keys, this kernel computes the actual attention, but only using those retrieved keys. It's essentially a specialized version of FlashAttention, but designed for this sparse input.
So it avoids wasting computation on the keys they decided to ignore.
Precisely. And they even tackled a subtle issue. Sometimes different attention heads might need very different numbers of keys. One head might find 10 relevant keys, another might find 1,000.
Ah, that could create load imbalance on the GPU.
Exactly. Their kernel smartly parallelizes the work across the GPU's streaming multiprocessors, the SMs, to handle this imbalance and avoid bottlenecks. It shows they really thought about the practical hardware implementation.
Very thorough. Okay, so they built it, optimized it. How did they test it? You mentioned they even created a new benchmark. Why was that needed?
Yeah, they realized existing benchmarks didn't quite fit their specific scenario, which is running multiple different user queries against the same long fixed document context. So they created prefix QA.
Prefix QA.
Right. It's important because it lets researchers properly evaluate these fixed context optimization methods. You have one big document and then lots of questions about it. It fills a gap.
How did they build it?
They took long documents, specifically ArcSIF research papers, and used GPT-4 Turbo in a multi-step process to generate question-answer pairs about those documents. The questions are designed to require looking up specific information within the long text. They got about 24 Q&A pairs per document on average.
So it really tests if the model can find the needle in the haystack using the fixed context.
Pretty much. It's a targeted benchmark for this exact problem.
And they use this plus standard benchmarks like LongBench and Ruler. What models did they test on?
Yep, they use Prefix QA, LongBench, and Ruler. They tested on popular models like Llama 27B with a CumQ context, LWM Text Chat 1M, which goes up to 1 million tokens, and LongChat 7B, another 32K model.
Okay. And how many centroids did they use in the experiments?
For the single-level approach, they typically used 5% centroids relative to the fixed context length. For hierarchical, it was often 1% level 1 centroids and 5% level 2. They also calibrated a global threshold to control the sparsity, how many keys actually get retrieved.
And that initial clustering cost, you said it was offline.
Right, a one-time cost. They reported it took about 24 minutes for 128,000 token context using 8 GPUs, which, if you're going to reuse that fixed context for many user queries, is pretty negligible.
Okay, makes sense. All right, the big reveal, the results. Did squeezed attention actually deliver? Accuracy? Speed?
The results are pretty impressive, actually. On
Yeah.
the accuracy front, they showed squeezed attention preserves accuracy remarkably well while being much more efficient.
How well?
On LongBench, using models like Gholami and LongChat, they achieved a 3.1x reduction in the KV cache budget, so using 3 times less memory for those keys and values with basically no noticeable drop in accuracy, less than 0.11 points degradation.
Wow. 3.1x less memory, essentially same accuracy. Let's pause there. What does that mean practically for someone running these models?
It means significantly lower costs to run inference, simple as that. Or, alternatively, you could potentially run models with much longer context than before on the same hardware. It makes complex tasks needing long context much more feasible, much more affordable. Things like analyzing huge legal documents or medical histories in real time start to look way more practical.
That is a big deal. What if they push the sparsity even harder? Less memory still.
They did. Even at a much more aggressive 90% sparsity, meaning they ignored 90% of the keys, which gave an 8x reduction in the KV budget, the accuracy drop was still relatively small, only about 0.5 points on average.
8x smaller cache for only half a point accuracy drop. That's incredible.
It really shows how effective the semantic clustering is at finding the truly important keys. They also compared it to other methods like Quest and found squeezed attention performed better, suggesting that semantic approach is superior to just looking at, say, attention scores from a previous run.
And the hierarchical approach, did that help too?
Yes, the hierarchical method managed to reduce the lookup overhead compared to the single-level approach while still maintaining that high accuracy. It confirmed that having those fine-grained centroids, level 2, is important for accuracy, but the hierarchical search makes accessing them efficient.
Okay, accuracy is preserved, memory is way down. What about actual speed? Did the system performance match the theory? Did users get faster answers?
They did. The optimized Triton kernels delivered real speedups. They measured more than 4x speedups on an NVIDIA H100 GPU. Specifically, about 4.3x faster for the prefill stage processing the initial long prompt, and 4.2x faster for the decode stage generating the answer token by token.
Over 4 times faster. That's definitely something a user would notice.
Absolutely. Faster responses are critical for interactive applications.
And the hierarchical lookup contributed to speed too.
Yes, they showed the hierarchical lookup itself sped up the centroid search part by up to 1.4x for a very long 512K context length compared to a flat lookup. So both the algorithm design and the careful implementation contribute to the overall win. It makes long context inference much faster and cheaper.
That really does sound like a significant step forward. But as always, no solution is perfect. What limitations did the authors acknowledge? Where's the future work?
They were quite upfront about limitations. One is hyperparameter tuning, things like the sparsity threshold, the number of centroids these currently need to be set manually, and the best settings might depend on the specific task or data.
So making that more automatic would be a good next step. What else?
The method is really designed for scenarios with a large fixed context known beforehand. It's less directly applicable if the entire context is changing dynamically with every single query. Maybe future work could try to accelerate the offline clustering part so much that it could be done almost on the fly. That's an open question.
Okay, makes sense. Focused on that fixed context use case. Any other limitations?
One other point is that it currently just discards the keys deemed less important. It doesn't try to approximate their contribution in any way.
So maybe you could get even better accuracy if you found a cheap way to approximate the effect of those ignored keys rather than just dropping them.
Potentially, yeah. That's another avenue for future research, finding ways to maybe incorporate a low-cost approximation for the discarded keys, perhaps allowing for even more aggressive sparsity while maintaining accuracy perfectly.
Okay, so wrapping this up, what's the big takeaway for you, our listener, and for the future of these large language models?
I think the big takeaway is that squeezed attention offers a really smart, practical solution to a major growing pain